again with another course named Telco Cloud, a very popular term in telecom industry since few years. Telco Cloud is software-defined, highly resilient cloud infrastructure that allows telco to add services more quickly, respond faster to changes in demand, and centrally manage their resources more efficiently. It is one of the key foundational components for transforming a telecommunications company into a digital service provider. Early telco clouds applied virtualization concepts from the data center into the network. With the advent of 5G, telco clouds building upon newer technologies like containers and microservices as well as hybrid cloud architectures. As they are deployed into telco clouds, containers and microservices will have to coexist with older virtualized network functions (VNFs) like EPC, SD-WAN, and security technologies that are running today. So this is brief introduction about it. Let us begin with what is Telco Cloud. Telco Cloud lets service providers run their network like a cloud. Telco Cloud supports agile and efficient creation and deployment of services. Its architecture connects public, private, and edge cloud infrastructure to enable seamless, DevOps managed environments for digital service provider. The foundation for this agile environment starts with a network functions virtualization (NFV) enabled platform, sometimes referred to as telco cloud infrastructure. Creating an abstraction layer for the telco network, this layer of the telco cloud includes modern hardware resources to support modular cloud-native network functions (CNFs) as well as virtualized network functions (VNFs). The telco cloud infrastructure establishes a software foundation for creating and delivering next-generation services. In addition to this software foundation, telco cloud requires automated orchestration to manage CNFs and VNFs across all software-defined resources. Telco cloud automation will manage service life cycles throughout the network cloud, the hybrid cloud, the edge cloud, and the IT cloud, software-defined data center or SDDC, in an integrated and consistent manner. Telco cloud automation is responsible for instantiating and delivering services to meet different quality of service QoS requirements seamlessly across network resources. With telco cloud automation, error-prone human activities like service provisioning are automated to remove complexity and optimize overall resource utilization. With a flexible software foundation and automation platform in place, the last layer of a telco cloud is the intelligence layer. This layer is chartered with service assurance and root cause analysis. By processing with streamed and normalized data from an end-to-end network, this layer creates dynamic network control as it continuously monitors and reacts to changing network conditions. Telco cloud intelligence makes real-time decisions about changes required to maintain performance and optimize utilization to close the automation loop and deliver improved customer experiences. Here I conclude this course. Hope you understand. Let's get into the topic. One of the primary drivers for digital transformation is the desire to break vendor lock-in and enable interoperable networks. In order to create multi-vendor environments, increase vendor competition, and drive standardization, many CSPs look to open source technologies as a part of their transformation. Bringing the benefits of standardization to valuable technologies like NFV, software-defined networking, and cloud-native microservices, open source technology empowers service providers in several ways. Overcoming the limitations of proprietary vendor hardware, this community-based innovation approach provides CSPs with the tools to control their network architecture and have the ability to continuously innovate in and on top of their network. This flexibility changes their relationship with their vendors while driving competition and, in turn, decreasing costs. CSPs reap secondary benefits from open source by providing a standardized foundation for hardened, differentiated vendor solutions. By leveraging open source solutions, vendors can turn their research and development resources to adding value to openly accessible platforms. Severing ties with legacy hardware solutions and turning to modern software-based technologies is strengthened with open source in the right places of a next-generation network architecture. Striking a balance between a foundation built on more modern, virtualized, and software-driven architectures with existing legacy resources, which are often still worth billions of dollars of investment, remains a challenging task. One tool that delivers value in open source throughout a telco network stack is Kubernetes. Kubernetes is a lightweight container solution to run multiple applications on a single server with a shared operating system. With its own file system, memory, central processing unit, that is CPU, and process space, Kubernetes is decoupled from the underlying infrastructure, which makes creating and deploying services across the data center, core, and edge easier. Kubernetes is an important tool to enable the cloud-native architectures that CSPs are building in their digital transformations. These microservices-based environments require containers to help them run more reliably, recover more easily, and use resources more efficiently. Many enterprises today have built a robust on-premises, cloud-like infrastructure using open-source technologies such as Docker, Kubernetes, OpenStack, and OpenDaylight with OpenFlow, promising greater interoperability and flexibility across heterogeneous hardware. Here I conclude the foundational component of a telco cloud. NFV is an architectural framework developed by the European Telecommunication Standard Institute industry-specific group. The framework provides a reference model where network functions are delivered through software virtualization with commercial off-the-shelf hardware. In this way, NFV moves away from proprietary, purpose-built hardware dedicated to a single service that is common in legacy telco network infrastructures. The result is transformed network that is agile, resilient, and equipped to deliver high-quality services. The NFV framework defines functional abstractions and interactions between the building blocks. Some of these abstractions are already present in current deployments, while others must be added to support the virtualization process and operations. Here the figure on the screen shows the reference model for an NFV-enabled telco cloud infrastructure environment with clear functional abstractions and interactions in the following tiers. Physical infrastructure. It represents compute hardware, storage, and physical networking as the underlying pool of shared resources. In addition, there are numerous other physical network devices such as switches, routers, element management system, and so on, making the execution ecosystem a hybrid virtual and physical topology. NFVI. The NFVI tier is delivering using the vCloud NFV platform. It delivers the virtualization runtime environment with network functions and resource isolation for virtual machine workloads. In NFVI, virtualized compute, storage, and networking are delivered as an integrated solution through data center. The NFVI is optimized for carrier-class workloads to enable the delivery of carrier-grade and resilient services. Infrastructure, high availability, performance, and scale considerations are built into this tier for performance optimization. Resource orchestration. This tier provides resource management capabilities to the NFVI tier. In this way, the NFVI can deliver a flexible infrastructure for life cycle management of workloads, network management, and resource management. The resource orchestration tier is responsible for controlling, managing, and monitoring the NFVI compute, storage, and network hardware, the software for virtualization layer, and the virtualized resources. The Virtualized Infrastructure Manager module manages the allocation and release of virtual resources and the association of virtual to physical resources, including resource optimization. The VIM also maintains the inventory of NFVI, including the linkage and relationship between components as they relate to an instance of a VNF or Cloud Native Network Function (CNF) workload. In this way, the VIM allows for monitoring in the context of a single VNF. Cloud automation. This tier provides a service management and control function which bridge the virtual resource orchestration and physical functions to deliver services and service chains including operation support system and business support systems. It is typically a centralized control and management function including embedded automation and optimization capabilities. Solutions. This tier is the multi-domain ecosystem that delivers software virtual functions as native VM functions. Such functions are composed in complex solutions to enable service offers and business models that CSP customers consume. Solutions can range from small branch office function including customer premises equipment to IP-based multimedia services, evolved packet core, multi-access edge computing, and more delivered as tenant slices across multiple clouds. Operations management. This tier provides integrated operational intelligence for infrastructure day 0, day 1, and day 2 operation that spans across all other tiers. The functional components within the operations management tier provide topology discovery, health monitoring, alerting issue isolation, and closed loop automation. As shown in the figure on screen, the telco cloud provides a common foundation for CSPs for their apps and VNFs. Beyond the NFV-enabled telco cloud infrastructure, transforming to enable the other components of the telco cloud, including automation and intelligence tools, is a process CSPs have been working on for the last several years. But there are several steps every project undergoes to achieve better agility. Hence, we can say the steps involved in this transformation are: first, virtualization. By separating network functions from their legacy hardware, greater flexibility is gained with lower operating expenses, OPEX, and capital expenses, CAPEX. Next is programmability. Removing human processes and enabling real-time control of network services provides agility, speed to market, and faster fixes. Next is orchestration. Full automation requires cooperation between the telco cloud infrastructure and the telco cloud automation to create efficiencies and provide on-demand differentiated services. Next is closed-loop feedback. Real-time monitoring and assurance to end-to-end services across a multi-cloud environment creates an intelligent, self-organizing network. Next is predictability. Applying artificial intelligence and machine learning can help future-proof a modern network while continually reducing costs and improving customer experiences. Providers building a telco cloud are building a single cloud environment that supports the creation and delivery of next-gen services with guaranteed performance and availability. With a focus on automation, this telco cloud joins the service provider's network with other cloud entities, that is, data centers, the public cloud, edge cloud, and private enterprise clouds. The telco cloud federates these cloud entities, providing visibility, orchestration, and management across the combined entities. The value is in the flexibility and agility of the telco cloud. It adapts to service providers' business needs as they evolve their operations and their businesses. With a single abstraction layer across multiple cloud environments, a telco cloud provides scalability, efficiency, reduction in complexity, and reduction in cost to allow service providers to do many things, including the following. First comes start with infrastructure as service offerings, then add platform as a service, software as service, and containers as a service offerings when it makes sense for their business. Second, securely host their own and third-party services in a multi-tenant environment. Third, quickly scale their resource pools up and down to meet new demands. Fourth, easily move workloads among data centers to ensure performance, improve resource utilization, and recover from faults. Fifth, tie customers into their data center resources. Sixth, support real-time, latency-sensitive applications and services as well as non-latency sensitive offerings. Next is support next-generation services such as immersive video communication services that require real-time video processing in the cloud and real-time communication applications that are hosted in the data center. Eighth, support service automation through one or more types of cloud stacks. Ninth, support scalable cloud management for more dynamic service provisioning and growth of industry services. Service providers have many years of experience meeting service level agreements for business critical services. In a telco cloud environment, service providers can offer end-to-end SLAs. These SLAs can cover first, performance requirements and benchmarks, second, actions in case of failure, third, data security, fourth, data privacy, fifth, compliance with industry accountability and accounting practices and policies. Sixth, audits and real-time analytics to monitor compliance. Seventh, ensure that covers incidents such as data center security breaches. Eighth, technical support. Ninth, acceptance period. 10th, termination clauses, risk management and assistance. 11th, end-to-end SLA integrity and accountability. All these SLA opportunities aside, SLAs in a software-driven network are very different from their hardware-driven counterparts. In a software-driven network, SLAs are met from a platform level, not a resource level, as they are in a hardware-driven network. The platform works in real time to manage the assurance of performance, leveraging all available resources, not by guaranteeing individual performance resource by resource. This means the way in which communication service providers scope projects and build requests for proposal RFPs need to change. Among many processes and procedures that need to be changed to support a more software-centric operating models, CSPs need to amend the way they engage their vendor partners. Is table stakes in a telco cloud. Building upon the momentum virtualization has provided, cloud-native approaches fully exploit cloud computing technology with a microservices architecture, leveraging containers to enable continuous delivery and dynamic management in multi-cloud environment. Cloud-native apps are designed, built, and implemented differently from traditional applications. Cloud-native apps leverage standardized events, logging, and services catalogs to streamline service creation and deployment. By standardizing service elements and running these elements in modular, containerized environments that are geographically distributed and centrally orchestrated, Cloud Native provides innovation agility. Cloud Native network functions are the next generation in the evolution of network functions. They extend the common approach of virtualized network functions (VNFs) to include cloud native principles, that is, containers, microservices, and orchestration. CNFs are typically built by using a microservice architecture, deployed in portable, predictable containers, and orchestrated with Kubernetes. The result in function that can be easily integrated with a continuous integration or continuous deployment, that is CI or CD pipeline, rapidly onboard and deployed, consistently managed with automation and dynamically scaled to meet changes in demand. Here is the path to use cloud native approaches. First is integrate any CNF while normalizing the containers as a service and infrastructure as a service layers with consistent telco cloud infrastructure. Under this, it includes first, workload vendor agnostic, second, standard compliant, third, unified design and onboarding. Second is automate complete CNF lifecycle management over any cloud and any hardware underlay. Under this, it includes first, CaaS deployment. Second, CaaS customization. And third, CNF LCM and configuration. Third, optimize telco cloud resources for the most demanding cloud native workloads, for example, virtualized radio access network or vRAN. Under this, it includes first, real-time operating system, second, optimized Kubernetes networking, third, burst to public cloud. Fourth, consolidate and integrate 5G service network functions for given markets across vendors and across sites. Under this, it includes service and slice design. Next is multi-cloud smart placement. And the third one is key performance indicator and driven LCM automation. Fifth, operationalize lean and agile DevOps practices across operational functions. Under this, it includes first, built-in CI or CD. Second is closed loop assurance, machine learning and artificial intelligence. Third one is vendor and site reliability engineer dashboards. Our next topic is DevOps mentality. In the end, digital transformation is meant to drive new service models. CSPs will have to become service innovators instead of relying on their vendor relationship to supply service innovation. Based on the current model of tying the service to the resources they require, the vendor innovation process is far too slow for the digital era. With DevOps methodologies, CSPs will be able to fail fast and create more opportunities more easily. While over-the-top OTT vendors have been succeeding with DevOps practices for years now, CSPs have been watching from a distance. With the telco cloud, CSPs now have a platform to leverage DevOps methodologies on the service network and are staffing up with their software teams to create value through new services as well as continually improve the scalable, programmable infrastructure. DevOps tools is the automation layer of the network are used to abstract service models, creating templates for service elements and their parameters. This portable way of describing services provides building blocks of technology-agnostic service component information, policies, and associated contracts. Common among CSPs, the model leveraged industry standards like yet another next generation and topology and orchestration specification for cloud application to ease deployment across varying technologies. By creating the service model, the automation layer can better maintain consistent outcomes. Orchestrating next generation networks. Automation is pivotal to business success and the operationalization of emerging 5G network technology. Meeting the ends of new technology requires different approaches to basic problems that now stem from increased levels of complexity associated with the joint management of new and existing network infrastructure. Automated, intelligent operations become business imperatives in bringing the gap between new and existing infrastructure and in managing 5G networks at scale. CSPs must embrace operations automation and look at every opportunity to reduce human intervention, resource operating expenses, and increase service agility. A shared infrastructure layer, dynamic resizing and movement of workloads, distributed topologies, and owned and leased cloud environments will drive the need for self-correcting and self-adjusting automation. In a cloud-native network made up of microservices and shared resources, the operational intelligence that CSPs need to manage, such as dynamic environments, must feature just-in-time analytics to trigger components and must offer a single line of sight for monitoring and resolution. With the shift to microservices and multi-cloud environments, the manual operation processes of current networks will no longer be feasible. Telco cloud automation tools include orchestration software engineered to accelerate the time to market of modern network functions, virtual network functions, and cloud-native network functions and physical network function while igniting operational agility through lifecycle management automation. Our next topic is service assurance. The telco cloud introduces new levels of complexity and a further distribution of resources. For these reasons, service assurance must evolve to address the changing nature of the network infrastructure as well as the new imperatives around the ultra low latency requirements of 5G, the emergence of customizable services, and the new paradigm of network slicing. Accuracy, speed, low latency, and error free operations of the telco cloud are critical to the success of the service provider's digital business. To compete and innovate successfully, CSPs need a real time, unified view of their infrastructure and network topology. Network operations need top level visibility across all domains to be able to monitor end to end network performance and customer quality of service. They also need to be able to drill down into their networks to get more granular insight into the causes of degraded performance or into possible ways to optimize the allocation of network resources. This calls for a more proactive approach to service assurance, which, with the emergence of artificial intelligence and machine learning, will evolve into predictive service assurance aimed at identifying network anomalies early before they negatively impact the network and the user experience. The characteristics of a modern service assurance strategy include the following. First, advanced analytics driven by machine learning for behavioral and reinforced learning. Second, distributed, graph-based topologies with hierarchical analytics. Third, real-time intelligence for dynamic optimizations and problem avoidance. Fourth, intent-driven capabilities replacing static rules with dynamic policies and operational intent. Fifth, extensible, model-driven, and open source to cater to declarative constructs and enable ease of integration. As CSPs prepare for the rollout of 5G networks, new tailored services, and continued network function virtualization deployments, the ability to monitor and immediately manage both the traditional physical infrastructure and the new virtual networks that overlay them as one seamless entity becomes mission critical. CSPs must evolve beyond reactive approaches with human intervention at each layer if they want to keep pace with the avalanche of new services, tighter cross-domain dependencies, and virtualized networks. Key service assurance requirements include the ability to, first, holistically monitor and manage networks at the service, virtual, physical, and transport layers. Second is automate root cause analysis of issues across all layers, including NFV and software-defined wide area network SD-WAN environments. Third, trigger closed-loop actions and remediations of problems via application programming interface, API integration with orchestration and operation support system tools. Fourth, prioritize issues based on correlation of service and tenant impact. Fifth, manage multiple tenants with multi-vendor solutions in a unified view. Sixth, drive SLA management with historical and real-time views, trending, forecasting, and adaptive alerting. Hope you all understood. Meet you in the next topic, operations and analytics. Similar to the change drivers for assurance, more intelligent analytics capabilities are required to combat rising complexity in cloud-native ready, hybrid networks, enormous network traffic growth, ballooning operational costs, and the creation of massive amounts of data. Complexity continues to increase because of the rollout of 5G technology and use cases that take advantage of the potential that this new wave of network capability offers. Existing systems and process fall considerably short in meeting business expectations that come from such a radical technology refresh and strategy change. CSPs understand the importance of managing day 0, day 1, and day 2 requirements with operational intelligence that can address the following. First, single pane of glass visibility across hybrid cloud environments. Second, dynamic discovery, cross-tier correlation, and huge multi-tenancy. Third, performance monitoring with predictive intelligence. Fourth, casualty analysis with prescriptive recommendations. Fifth, embedded demand forecasting and cost analysis. Sixth, closed loop automation for dynamic optimization. A telco cloud requires a robust solution to manage CSP operational processes across a hybrid virtual and physical environment. Traditional approaches to integrate operational intelligence across the ecosystem with the hardware-based vertical solutions are neither sustainable nor viable. Streaming analytics is another important telco cloud capability that allows user to continuously query a stream of data and perform statistical analysis on this data stream as it's moving through the system. Conditions and patterns can be detected very quickly, and multiple streams of data can be correlated for new insights. Streaming analytics provides time-sensitive processing and is suited for the rapid analysis of time series data streaming from devices, Internet of Things IoT sensors, transactions, applications, and web sessions. Key streaming analytics use cases include the following. First, customer experience. Delivering superior customer experience is a key driven for competing in the cloud economy. CSPs can use streaming analytics to understand their subscribers' experiences. By cross-correlating various metrics such as voice and data performance, time of day, services used, cell site association, and application used, CSPs can more readily determine the quality of experience (QoE) of their customers. Network errors and call quality can be compared to customer survey data such as Net Promoter Score to better understand any relevant correlation between them. Second is marketing. Mobile network operators (MNOs) can use the real-time intelligence provided by streaming analytics to run location-based mobile marketing campaigns, giving them the ability to target advertisements to an anonymized set of subscribers when they enter specific geographic areas. MNOs can also offer proactive roaming incentives based on subscribers' real-time roaming statuses. Anonymized information on density and frequency of subscribers in a particular location can be offered to content providers and advertisers. Third, operations. Using streaming analytics, MNOs can measure real-time data quality of service to improve network operations and customer experience. They can correlate the quality of the long-term evolution (LTE) and voice over LTE (VoLTE) network. How many calls or messages are succeeding, failing, or degrading within a certain cell site with the specific models of phone, operating system, time of day, and so on. By understanding real-time cell site traffic usage such as volume, density, and errors and attachment success rates, MNOs can better optimize their radio access networks and core networks. Our next topic is offering intrinsic security and data privacy. Security and data privacy issues are of paramount concern for CSPs and their enterprise customers and end consumers. To effectively address these issues, the telco cloud must be designed with security and data privacy built in rather than as bolted on products or services. This approach is necessary due to a highly dynamic nature of cloud and virtualized environments. VM workloads, VNFs and CNFs and containerized services are rapidly and frequently provisioned, deprovisioned, and moved in a cloud environment. Security and privacy must therefore not be tied to a physical location or logical construct such as an IP address, but instead must be an intrinsic part of the resource to be protected. Data should always be encrypted, whether in transit or at rest. Technologies such as microsegmentation can be employed to effectively create a perimeter around individual resources in the telco cloud, each with its own granular policy defined and enforced as needed to ensure the security of the resource. And individual security elements can be deployed as VNFs themselves as part of a larger security apparatus within the telco cloud.